Okay, hello everyone. This is my second effort at doing the proof from first principles video. The volume, I had no sound on the other one. I'm so sorry. It's so annoying as well. I thought I'd done a good job, but then no sound on the video. So let's have a go at this. Now, key thing is for these kind of ones, firstly, I don't think they'll definitely come up or anything like that. I think it's more likely they'll get you to do sine and cos. But I'm going to show you that sec x differentiates to sec x tan x from first principles. And then if I've got time, and I've only got about 10 minutes, I'll try and show you that tan x differentiates to sec squared x from first principles. Now, first things first, always use the first principles formula if you're doing this. So we're given fx equals sec x. And what we want to do is use this formula, therefore, to write f dash of x is the limit as h tends to 0 of f of x plus h minus f of x over h. Now, the thing is, we're actually told, and keep writing down this limit as h tends to 0 bit, we're told that f of x is sec x. So we're going to do sec of x plus h minus sec of x over h. Now, the whole point of doing proof from first principles is you start off with something where you're going to end up with 0 divided by 0, because if h was 0 at the moment, you'd have sec x minus sec x, which is 0, and then it would be divided by 0. And we want to avoid 0 divided by 0 because that's called an indeterminate form. In other words, you can't determine what it equals. We're going to put it in a more convenient form where we can determine that. And it almost always involves cancelling the h on the bottom. Yeah, every single time really. So that's what I'm going to try and do. Now, I don't really know what sec x is, so I'm going to write it as cos of, yeah? Now, 1 over cos x plus h minus 1 over cos x over h, yeah? Now, I'm not particularly happy with this, but first thing I'm going to do is I'm going to combine those fractions. So I've got the limit as h tends to 0 of, now all I'm doing here is the standard way we subtract a fraction. That times that minus that times that over that times that. So I'm going to have cos x minus cos x plus h over cos x plus h. And then I'm like dividing that by h. But if you ever take a fraction, 5/6, and you want to divide it by h, for example, that's exactly the same as timesing the bottom by the h, yeah? Because of the way fractions work. Think of it as h over 1, it's going to become times by 1 over h. So it's 5 over 6h, yeah? So in other words, this h ends up on the bottom here, yeah? And that's what I want to cancel. That's what I really want to cancel. So that's what I'm going to try and do. Now the trick is, don't expand the bottom. Just expand the top using compound angle formulae. So you're going to have cos x minus, okay, open the bracket, cos x cos h minus sin x sin h. And that's just a standard compound angle formulae for cos. All over h cos x plus h. Cool. Okay, what do we get next? Well, okay, we can now use small angle formulae, which you always use in proof from first principles involving trig, every single time, because h is getting towards 0, so it's very, 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 very small. And this is the whole point of these. We're basically going to try and deal with it as if h is a quantity so that we can cancel it on the bottom, so we avoid that indeterminate form of 0 divided by 0. Now, what are we going to have here? We're going to have cos x multiplied by 1 minus h squared over 2. That's just a small angle formula for cos. I can only do it on the h's. I can't do it on the x's. X isn't going to 0. H is going to 0. So I can only do it on cos h and sin h here. So this is going to become minus h sin x, yeah? And it's all over the same stuff as it was before. Don't bother expanding the bottom. It will do you a favour, trust me, if you don't, yeah? Okay, so what have we got here? We've got a limit as h tends to 0 of, okay, well, after you expand those, you're going to have cos x minus cos x, but then this is going to become, after you times that in, you're going to have a minus h squared over 2 cos x, but it's minus minus, so that becomes plus h squared over 2 cos x. And the same here, that becomes a plus as well after you expand these brackets, so it becomes plus h sin x. Now, I was really happy when I saw that result when I was working through this, because it meant that I could cancel the h on the bottom, yeah? Now, I'm not talking about the h in the brackets, because that doesn't scare me so much, because if that h was 0, you'd be left with cos x, and cos x is fine, yeah? It's only if you're dividing by 0, which you want to avoid, yeah? So what I can now do is I can cancel my cos x's, and I'm left with the limit as h tends to 0. Notice I always write that down no matter how much it's annoying me, and it is. I can now cancel this h and this h with that h, leaving h over 2 cos x plus sine x all over cos x plus h. Yeah. Now, one of the things which annoys me when I teach limits to single mathematicians is the fact that none of the textbooks actually include a decent list of the algebra of limits. Yeah, I think this is massively useful and massively important. Like, I don't think it's necessarily obvious either, but you can treat limits really casually when you're adding. Yeah, you can just find the limit of the first term and the limit of the second term. You can do the same with subtraction. You can even do it with timesing and, in this case, dividing. In other words, yeah, if you've got a fraction and you're finding the limit of the fraction as x tends to a certain value, well, that's the limit as x tends to a certain value for the top divided by the limit as x tends to a certain value for the bottom. What that's saying to me is I can find the limit for the top and the limit for the bottom and then evaluate. Yeah, that's not, that's not too much of a problem, because what you can see now, we're now in a situation basically where when we make h equal 0, we're not dividing by 0. We've avoided the indeterminate form. This bit's going to disappear. Yeah, so I'm going to deal with a limit now. This is going to become 0 times cos x, which is just 0, and so I'm left with sine x on the top. And on the bottom, when h tends to 0 here, you're going to get cos x, and so that's cos squared x, yeah? Now, I would like to point out, you really should justify this in the exam. You want to say, as h over 2 cos x tends to 0, as h tends to 0, and cos x plus h tends to cos x, as h tends to 0, yeah? I know we're stating the obvious, if you ask me, but they want you to state that, they really do. Now, this is actually, because it's sine x over cos x, which is tan x, times 1 over cos x, which is sec x, this is the same as sec x tan x, as required. Yeah, and just to show you, just in case, because I figure like either one of tan x or sine x will come up. I'll just quickly prove that tan x differentiates to sec squared x. I don't think it will come up. I think we're worrying about nothing here, but just in case it does, be one of the 5% who get it right, because very few will get these right in the exam. There's no examples in the book like this, sadly, and so I'm guessing that it won't come up, but you never know. Yeah, it's better to be better to be prepared. Where's my pen? Where is it? This one? Yeah, here we go. Okay, so let's say you had f of x is tan x. I'm going to try and show that tan x differentiates to sec squared x from first principles. Okay, f dash of x is f of x plus h, which in this case is tan of x plus h, minus f of x, which in this case is tan x, over h. Yeah? Oh, and I've left out my limit. Let me put that in. Limit as h tends to 0 of all of this. Yeah, apologies for my messy handwriting as well, it probably really annoys you. So this is the limit as h tends to 0 of, now let's just use compound angle for tan, which is tan x plus tan h over 1 minus tan x tan h, tan x tan h, minus tan x all over h. Yeah, I think I'm now going to do a similar trick to what I did with the h last time. I'm going to say, well, both these terms need to be divided by h, don't I? So let's put the h on the bottom. And it's always about cancelling a h on the bottom of a fraction, these things. Okay, tan x plus tan h over h times 1 minus tan x tan h minus tan x over h. Yeah? Now, it's the h's on the bottom I want to cancel. You can see I've already done this question a second ago because the sound wasn't working. Okay, so what is this? This is a limit as h tends to 0 of, okay, right, let's actually combine these fractions. So this one needs to be times top and bottom by 1 minus tan x tan h. So we're going to have tan x plus tan h, so I'm going to try and write this as a single fraction, minus, okay, I hope you can see what I'm doing here, 1 minus tan x tan h multiplied by tan x, yeah, all over h times 1 minus tan x tan h. Okay, so really all I've done there is I've times this one, top and bottom, by this whole bracket, 1 minus tan x tan h, top and bottom. And then I've got a common denominator, so I've combined them. Now what you'll see, once again, is the terms without a leading h in front of them cancel. And so you're left with tan x minus, now can you see that's going to times in there to give us, I'll tell you, I'll write it out, just so it's real clear. Okay, when I times the tan x into this bracket, so I get minus tan x, and then plus tan squared x tan h, yeah, all over h times 1 minus tan x tan h. Now what I should have done is earlier used the small angle formulae for tan, because you remember me saying you always use small angle formulae. That's why I'm taking slightly longer than before. Okay, so let's use small angle formulae now. Let's cancel those tan x's. We're going to be left with h plus h tan squared x over h 1 minus h tan x. Yeah? Okay, we cancel the h's. That's the whole point. That's basically the trick in any question like this. You want to cancel the h's on the top and the bottom. Like, you can be left with some h's, but just ask yourself, am I dividing by 0 when h becomes 0? Yeah, that's what you really want to ask. Now, let's ask ourselves the questions, because look, we've still got a h on the bottom. Surely that's a problem. Well, no, because if we make h 0 here, we end up with 1 plus tan squared x divided by 1, which is just 1 plus tan squared x. We've avoided the division by 0, or 0 divided by 0, because in every single one of these questions you will start off, if h is 0, with 0, tan x minus tan x, divided by 0. It's an indeterminate form, it's what we're trying to avoid. Now that's not sec squared, but is it? Oh yes it is, because 1 plus tan squared is sec squared x, and it's proved. Okay, hope you enjoyed the video and found it useful with the audio this time. Thank you for the question, Abby. It's a great question. Like I said in the email though, don't worry about the mega difficult stuff too much. Try and balance easy questions with hard questions in your revision, because there'll be some nicer questions and some nastier questions. And if this came up, I'd definitely describe it as a nasty question, but I definitely wanted to do it because one of these days it will come up, one of these questions, and you'll be the one really prepared for it. So yeah, excellent. Okay, bye bye and thanks for listening.